Okay, good afternoon, friends. So let's start. We have been talking about the inelastic neutron scale measurement to study the phonon excitations. So okay, I'd like to clear some of the issues that we did not discuss in the resolution. Is so see, suppose this is a typical phonon dispersion curve. This is the wave vector and the frequency. And then let's say typical, this is a phonon branch that we are looking at. Now, around some point Q and around some frequency omega. So we make a measurement in the experiment around the transfer Q and the energy transfer omega. Now, actually, on the instrument around Q, you will have some plus or minus dq, for example, which is the resolution, and similarly omega also, you will have some plus d omega. So the resolution is actually a four-dimensional function, 3 of the wave vector and 1 of the frequency. And in this, and it is actually called a resolution ellipsoid in the four variables. Now, for example, if I am, just think of it that you have a resolution ellipsoid which looks like this. Okay, so we are actually in q omega space, and the small q or capital Q, those are related. So we said capital Q is nothing but a reciprocal lattice vector minus the vector Q. And now assume that I am doing a constant Q scan. So I am going to scan at different points. The spectrometer will be set at different points, and I measure the intensity. Okay, so if you plot the intensity as a function of along these points along the omega, then you should get a peak corresponding to the frequency. So this is just the intensity, and that is the omega. We are scanning it. Okay, that's a scan. The scan is a constant Q scan, so the Q is constant, and I'm only varying the energy transfer and measuring the intensity. So that gives a peak. If this is a resolution ellipsoid, so at every point you take the resolution ellipsoid and the convolution of the resolution ellipsoid and the phonon dispersion surface, that will give you the intensity. If there is no overlap, no intensity. If there is an overlap between the dispersion surface and the resolution ellipsoid, then you get an intensity. Okay. Now, on the other hand, if the ellipsoid were, let's just see that. Suppose I'm actually measuring at at minus q. Okay. In the minus q direction also, we know that the phonon's frequencies are symmetric with respect to q or minus q, whether you have, depending on whether the phonon is propagating in the plus q direction or minus q direction, the frequencies are same. But if I measure here, then and with the same kind of resolution ellipsoid, then you can see that this kind of function will have a different overlap than here. Here, because if this resolution ellipsoid is nearly parallel to the dispersion surface, then the overlap will be for a very narrow region in frequency. On the other hand, if it is at a different angle, say almost perpendicular, then you will get a fairly broad intensity pattern. So these are two different scenarios. Now here, to give you an example, suppose Q is equal to 0.3 of along the A star direction. Okay, let me show what this phonon is. And as we said the other day, it's possible that I choose a G which is say 0.40 and small q is 0.300. Okay, these are the components along the three reciprocal lattice vectors A star, B star, and C star. And so capital Q is minus 0.340. Okay. Now I could also measure it in the other direction where Q is not plus 0.3 but minus 0.3. Then the capital Q would be 0.340. So you can get the same frequency at these two different settings, but in one case you may get a very narrow peak in omega. In other case, you may get a very broad peak. So there is a very important role of the resolution function in making phonon measurements. So we can we call one of these settings as a focusing geometry and another a defocusing geometry, and therefore this is very important. In the actual experiment, we normally have some calculation or some standards of what kind of Q values, whether you should be, for example, taking minus 0.340 or plus 0.340. One of these is favorable for from the resolution point of view, and the other one is not. Okay, so this is now this resolution function depends on many of the instrument parameters. For example, what kind of monochromator crystal you have, or what kind of analyzer crystal you have. What are the collimation angles between a monochromator and sample, and so on. So these various issues determine the okay. This mouse has some issue, I think.
No, this pen you have to put down. Then it will work.
Oh, the pen should. Thank you. Okay. So, see, the resolution function depends on the detailed characteristics of these for example, the mosaic spread of this, you know what mosaic spread is? Mosaic spread, you probably know already, that the crystal planes are not all, it's not perfectly, it's not an absolute perfect crystal where all the atomic planes are exactly parallel with each other. Is usually small misorientation amongst different mosaics or small blocks in the crystal. It is still a good single crystal, but there is a mismatch typically of a few minutes, could be half a degree or a degree. And that mismatch is really very important and essential to get a good neutron intensity, because otherwise your intensity would be extremely poor. If you try to have an extremely tight resolution. So we really purposely have to spoil the resolution to a certain extent so that we get a good neutron intensity from the monochromator and also from the analyzer. So these are the typical numbers. And typically the mosaic planes or the break planes in the monochromator in different mosaics, there is a spread of about half a degree or 1 degree. And typically these angles being what they are, we have a few percent of the energy as the resolution, and similarly there is also a few percent of resolution in the wave vector space. Okay. Now the next question that was already asked by somebody: how do we choose the G values in the scan? And we said, okay, it depends on this function. So let me amplify it a little bit again. There are a number of issues here, and okay. So you see, in the form factor, is the main important terms we have is q dot xi, that is the eigenvector. Okay, that's an important term. And then you also have the normal term that we have in case of even diffraction, and you have some overall terms. There are other terms here. Okay, the expression is already given to you. Now, if for an acoustic mode, the value of the eigenvector component or the polarization vector is really same for all the atoms. And so that means if for all the atoms this term is nearly same, then the structure factor will correspond to some, and that is same as the break structure factor. Okay, so for acoustic modes, we get the similar dependence as a function of capital Q for, sorry, I should say G here. Okay. This needs to be corrected a little bit. Okay. Yeah. And we said Q is equal to G minus. So for acoustic modes, the one phonon structure factor and the Bragg structure factor tend to be very similar. Okay, these are general thumb rules. However, for optic modes, what happens is that the vibrations of atoms inside the unit cell, they can be out of phase with respect to each other. It means for some, depending on the K, for some K it may be positive, another K it may be negative. And in such a case, you get a cancellation of terms. So all the terms will not submit like this, but you might have a change of sign here, and which means that the reflections which are very strong means a very strong reflection for a G will not be very strong for the optic mode. So the optic mode usually it's the other way, that if you have a strong Bragg reflection, you get a good intensity for acoustic modes. However, for optic modes, you get good intensity at points where the Bragg reflections are not very strong. Okay, this is a very general thumb rule, but as you can see, this will apply only when you have a fairly simple structure in which you can talk of some simple acoustic modes and simple optic modes, not when you have a very large number of modes which tend to have a very complex eigenvectors or phase with different atoms. Okay, so we will come back to this issue slightly, but for example, here what we can say is that sometimes there are pronoun branches which are like this. Okay, and this is at the okay. This is Q. This is the zone center. Let's say this is a zone boundary, pi by A. So extend it to 2 pi by A. That then you know that this is another effectively another zone center, and the dispersion curves would look like this. But that's very interesting. That interesting thing to notice here, that you can talk as if there's a branch here which is with a small gap is crossing over in another zone. This is first Brillouin zone. This would be a second Brillouin zone. Okay, so it does happen quite often that if I'm measuring a phonon starting with at this end, let's say at around say 400, and okay, so by the time I'm here, it may be, or let me say 040. This is assuming it a transverse phonon, or well, it doesn't matter. So let's say this is a longitudinal phonon, and Q and G are in the same direction. Both Q and G are in the along direction. So here, what is the capital Q here? It may be so. Let's say it will be this number is actually 0.5 in terms of 2 pi by A. So here the Q is 0.5, and so capital Q at this point would be 3.500. Okay, 400 minus 0.500. And suppose if I were to continue in the same way, then I'll end up coming here, reaching here as 300. Now I don't know whether you fully understand this part, but at Q equal to 0, my G is 400 and Q is 000. At the zone boundary, my G is still 400 and Q is 0.500. So G minus Q is 3.500. When I'm reaching here, okay, notionally I may say it is Q is this much, but See, if I say small q is 100, now you might say that this is outside the first drilling zone. So actually, instead of working this way, let me work out this way. So normally one would measure this branch around 300, and but in the opposite direction. So okay, so this is measured at 300, and then this point is at 3.500. So the idea is that we can continue phono dispersion measurements from zone center to zone boundary, from zone boundary to another zone center on a different branch, and so on. This kind of things are often done. If the phonon eigenvectors very smoothly across the Brillouin zone. This is probably not very clear, but then I should like you to ask questions so that we can clarify again in a tutorial. The important things that we've talked about so far here, in detailed phonon measurements, the first thing we mentioned, it is important to see how the resolution ellipsoid is, whether it is, what is the orientation of the resolution ellipsoid, and we try to choose the vectors in such a way that we are parallel to the resolution ellipsoid. Second is choosing the value of G. It can be done on the basis of some simple arguments, and often one starts with the values where the Bragg reflections are very strong, and then go over from a strong reflection to a weak reflection. The acoustic mode is measured around a strong Bragg reflection, and the optic mode may be measured around a weak Bragg reflection. So here I'm assuming that 400 is a strong reflection and 300 is a weak Bragg reflection, which is often the case. It might even be absent in certain structures depending on the kind of structure we have. Okay, that's another story. Let me just okay. One more simple thing that one can mention. See this structure factor again. Oh, sorry, I did something wrong. Okay, good. See, one more thing that, again, I just want to draw attention here. So the one phonon structure factor we said is has this kind of terms, and the phase term. I didn't write here the de Broglie factor and other things, which you already know. Okay. Now think of it. Suppose you have a phonon in which a molecule, let's say that's my unit cell, and let me think of it. There's a molecule here. It could be okay, and the nature of the phonon that I'm looking at, it is a rotational or librational phonon, say, in which that's a rotation of the libration of the molecule about some axis. Okay, so now in such a case, if now the Q is small, let's say, so that the phase changes are Q is so small that or the corresponding wavelength is large, then we normally know that if I take the sum total of the displacements of all the atoms in a rotating molecule, then they'll come out zero because they will simply cancel with each other. So for a rotational phonon, this term tends to be small or zero for small q values. And these will not vary much because if q is small, then the corresponding changes are also really small. So that means the rotational phonons, or what we normally call the librations, are not measurable in a good way at small q values. So for librations, we normally choose very large large G vectors. And translations, of course, what I just mentioned, acoustic and optic modes, the G need not be extremely large. Okay. There are some more things about the how we choose G and so on. See, for example, for diffraction, if you have a simple structure like an elemental solid or a diatomic solid like sodium chloride, so suppose you have either a sodium or sodium chloride simple structure, in that case, all the atoms are located at some high symmetry sites inside the unit cell, which means that these quantities x of k are typically like 0, 0, 0 or half of 0 or half 0, 0 or something. Okay, when you have values like this, all that, or in case of silicon, for example, the atoms are at quarter, quarter, quarter. So when you have the atomic positions at such high symmetry sites, in that case, the structure factors have some kind of a periodicity. The structure factors will just repeat up depending on what these numbers are. Okay, that can be calculated. So if you calculate the structure factor for simple solids, then even for Bragg reflections, depending on as a function of G, you will get some periodic behavior of the structure factors. The same kind of thing also holds for phonons. The only major difference is that you have to, okay, there in the diffraction also, you do worry about the de Broglie factor. So for large value of Q, then the intensity reduces, but otherwise the basic function repeats. So that is useful. And well, okay, I just mentioned about this extended zone scheme. So typically, for example, we made a measurement in a simple crystal. I think I just mentioned you. Okay, this kind of system I had mentioned to you. It's a body-centered tetragonal structure. And the value of G that we typically used were like 040, 310, 130, and that kind of G values around which the measurements were made, and so on. So that seems to work fairly well. Okay, that's another very important issue, that is about what is the use of group theory in phonon measurements. Okay. See, here's a typical example, the crystal I just mentioned. It's a body-centered tetragonal structure, and the large number of phonons you have, they can be divided amongst various group theoretical classifications. So you are probably familiar that in Raman scattering, the modes are assigned as, for example, AG, AU, or so depending on the symmetry. Now, what is that we look at. So okay. See, now what happens is again this in a crystal you have various point group operations. So typically you have let's say the of course there's an identity operation. This is where every atom. So if you have a number of atoms, any atom remains where it is if you apply the identity operation. So this is something like represented by a matrix like 1, 1, 1. So no change. Similarly, you can have a two-fold rotation, let's say about the c-axis, and so x and y change sign, and z doesn't change sign. So you an atom which is here under a two-fold rotation about the c-axis, it will come to this point. Similarly, of course, in this case, even you have also things like inversion, and the product of these two operations would be a mirror, and so on. The idea is that we have various point group operations inside in a unit cell, and the phonon eigenvectors of various atoms. So if there are a number of atoms in the crystal, as we said, k equal to 1 to n. So let's say there are 4 atoms. Now the phonon eigenvector components for the 4 atoms are often related also by some kind of symmetry operations. Depending on, of course, the number of factors, depending on what the Q is and so on. And now once that happens, the large number of phonons that you have, like in this case, there will be 12 phonons, 4 into 3, 12 phonons. These phonons can be classified under what we call different group theoretical representations. Okay, this is irreducible representations. Okay, so all the phonons are not in just one category, but they are divided in different representations. And so say typically, let's say these are denoted as if there are 4 of them. So you can say these are 4 categories, or there's a 4 classification. So all the 12 phonons will be divided amongst these 4 different categories. So each of them may have certain number. It could be, for example, 4, 2, 4, 2, 4 under tau, 4 of type tau 1, 4, 2 of this, and so on. Now, this is a very important classification because it tells us 2 things. One, what is the symmetry of the phonons which belong to this representation? So there is certain symmetry. It could be, for example, this displacements are symmetric with respect to inversion, or antisymmetric with respect to inversion, which means the displacement of, for example, this atom and this atom, how they are related, whether they are symmetric with or antisymmetric, equal or different, and so on. So we have certain information about what are the symmetries of the phonons belonging to each representation. Now, this information, it is very useful to decide what kind of G values these can be measured. Quite often, the phonons which can be, the G values at which tau 1 can be measured, maybe tau 3 cannot be measured. So there are certain selection rules coming from group theory. Depending on the value of G, only certain representations, phonons belonging to certain representations can be measured. Okay, so that is again a very useful thing. These kind of calculations have to be done in advance before planning a detailed measurement. So for example, in this case of zirconium silicate, it's not an extremely complex structure, but all the phonons that exist in the directions Q100, they can be classified in terms of 4 different representations, group theoretical irreducible representations, and they can be measured in a way quite separate to each other. It's not as a rule, but depending on the point group symmetry, it is possible to identify the values in the reciprocal space, the G vectors, where you can measure one of them exclusively, or only a combination of 1 or 2 of them, but not all 4. Okay, so that way it's a very useful method. I must tell you that measurement of phonon dispersion curves is a fairly involved process, requires a lot of preparation about how to systematically measure different phonons. But fortunately, nowadays the interest is restricted quite often to specific branches which have some unusual behavior, or for example, one may be interested only in phonons around this point. And that may be because the phonons around this point have some relationship with some other specific thermodynamic properties or phase transitions. Could be phase transitions, well, that I'll probably tell you separately. But around phase transitions, these phonon frequencies change very significantly as a function of temperature or pressure, and that is why and its eigenvector is closely related to the nature of phase transition, the way the atoms displaced in going from one structure to other. It particularly applies to second order phase transitions, but may be of interest to even other transitions also, because it will signify how a given parent crystal structure becomes or tends to become unstable. So that is one way. Another kind of situations, for example, that there may be certain phonons which contribute very strongly to, say, phenomena like thermal conductivity, being highly anharmonic, or so one is interested in measuring those phonons and their lifetimes and dispersion around it, which are key components in estimating the thermal conductivity contributions. Others could be, for example, anomalous thermal expansion, where certain highly anharmonic phonons could have a very important role in determining the anomalous thermal expansion or negative thermal expansion. So these are some of the things. It could be that other situation is that a phonon is highly interacting with the electrons, has a large electron-phonon interaction, has the wave vector have certain relations with the Fermi surface, and so there are things like cone anomalies, or a strong electron-phonon interaction could also mean that this phonon has a large contribution in, for example, superconductivity in the BCS mechanism, and so on. So in many of the crystals, what we are trying to say is that in many of the crystals, specific phonons may be of very high interest. So one may not be interested in all the phonons, but only certain specific phonons, and trying to measure how the frequencies and their lifetimes and the dispersion around it vary as a function of, say, temperature and pressure. However, even in that case, one needs to identify proper G values around which they can be measured. One needs to identify the instrument parameters, what kind of resolution it has, how is the resolution function, the orientation of the resolution function in the 4-dimensional space of wave vector and energy, and so on. So what are the group theoretical details of that phonon, which are which which are essentially characteristic of the symmetry of the crystal structure and may not depend heavily on the nature of the interatomic force field or interaction between atoms. So these are some of the things. There are a few other things that I should like to mention. Yes. Okay. Yeah. See, this term here, as I said the other day, this is when the neutron energy loss, for the neutron energy loss, that means neutron loses energy and you create a phonon. In that case, the probability of scattering is proportional to n plus 1. Okay, this should have been, plus is for the neutron energy loss. I'm sorry, that's a small mistake here. Plus is for neutron energy loss. Or let me just... Okay, so for neutron energy loss, when EI is greater than EF, then the intensity is proportional to n plus 1. For the other case, when EI is less than EF, that is energy gain, the intensity is proportional to n. Okay. Now, if the temperature is very small, then n is negligible. So you can see that this phonon would be measurable only in these cases. So at low temperature, now when we say low temperature, what we actually mean is that if h cross omega is much larger than kT, so for energies which are much larger than kT, or in other words, when the temperature is small compared to the phonon energy, in that case, the n is negligible, and therefore such a phonon can be measured only in neutron energy loss. However, high temperature, so these are in fact very similar to the Stokes and anti-Stokes in Raman scattering. But here, yes, so we have to make measurements typically in the neutron energy loss mode, but we can also do it in the energy gain mode at high temperatures or for frequencies which are very small. Okay, that's one. Second is yeah. Other thing is we also said okay now. Yes. This is about the coherent and incoherent scattering. So, you see, in one phonon structure factor, as we had mentioned sometimes, essentially it's a collective dynamics, and therefore it is only the neutron scattering, coherent scattering length or the coherent scattering part that contributes to the one phonon structure factor, and the incoherent scattering does not. But then there are certain atoms, for example, I think I mentioned hydrogen and deuterium. The hydrogen atom see, I think it probably mentioned that this is as an example, hydrogen has a very large incoherent scattering. and much smaller coherent scattering. So that means there is a large incoherent scattering will occur, and that will give you a very large background, which is in fact extremely large. The incoherent scattering cross section is in the range of 80 bands, as against a few bands for the coherent scattering. So if you wish to make phonon measurements in solids containing hydrogen, then it's not a good idea to use hydrogen, but often we deuterate the sample, that means replace the hydrogen with deuterium atoms. The chemistry does not change very significantly, although the mass of the nucleus changes and the frequencies will change to that extent because mass is important. But the measurements are most often done in deuterated samples, whenever, particularly for the one phonon structure factor or what you need to do. So that's one important thing. This can also apply to lithium, for example, where lithium 6 and lithium 7. Lithium 6 has a large absorption, so it is advisable to use lithium 7 isotope only if it's possible. But then this is a less important thing. Then mostly it is important for hydrogen deuterium. And so this is one thing that we have to worry about. There are certain other issues. Yes, there are certain other issues here. For example, let's take this monochromator crystal. See, typically, suppose my monochromator is okay. Let's say monochromator is copper and the plane is 111, and at certain Bragg angle, it gives you certain wavelength lambda I or corresponding to energy which is EI. But when I'm setting this, copper 222 also reflects, and that gives at the same angle, it will give a wavelength which is half. So if I've chosen certain wavelength for the next higher reflection, the D spacing is double. And no, so the D spacing is half, and so the wavelength is 2D sine theta equal to lambda. So the wavelength is half, or the energy is 4 times. Okay, so these are called higher order reflections from the same monochromator, and therefore when I'm doing the experiment, I have to be careful, or I have to be conscious about the fact that the neutrons which are incident on the sample are not only lambda I, but also lambda I by 2. Now, this situation may be helped if I, let's say, the neutron spectrum in the reactor is a Maxwellian spectrum. So, you see, if I take the spectrum of neutrons coming from the reactor, the intensity of reactor, the neutrons coming from the reactor. Okay, this follows a Maxwellian spectrum. And in the Maxwellian spectrum, normally I would have chosen a wavelength which is say somewhere around here. Okay, that is my lambda I. So lambda I by 2 will be here, and the intense. So it may so happen that if I have chosen a wavelength such that the reactor itself has a much less number of neutrons for half the wavelength, then maybe it's not a very serious problem, and quite often this intensity may be 1/10 or even much less than that. But I still have to be careful about it. So these are called issues related to higher order contamination. Sometimes these issues are also resolved, and the same thing can happen with analyzer also. Quite often it's a pyrolytic graphite analyzer of say 002, and you can have also 004 coming in. But here what we do often, actually in all cases. So this is one way that I can choose a wavelength which is such that the reactor has much less neutrons of smaller wavelength. Other thing is to use a filter in the beam. So often a filter is placed here such that it will filter off the neutrons of specific wavelengths which are undesirable, and that may work. A third option is instead of copper, for example, if one uses silicon, say 111, then we know that by symmetry, silicon 2 reflection is absent. Okay, that's because silicon atoms are at 0, 0, 0 and quarter, quarter, quarter. So silicon 2, 2, 2, the structure factor is 0. And so there will be no second order reflection. Third order may be there, but by third order, the intensity in the neutron intensity coming from the reactor may be much too low. So these are some of the things that we have to be aware of when we are measuring phonons, because it should not happen that we are looking at a false signal, not coming from the kind of phonon that we are looking for, but because of these instrumental issues. There's also a much less worrying about situation like where you might have a multi-Bragg reflection. So I may think that there is a single reflection 111, but under some conditions, more than one reflection, there is a multiple scattering in the sample, and that can be two consecutive Bragg reflections. But that's usually not the case. We don't use a very thick sample and thick monochromator, and so those issues are taken care. So these are practical issues measuring phonons in from a single crystal in a reactor, and there are similar issues also in the when you do it with a time of flight spectrometer. Okay. But anyway, today we have spent so much time in looking, in discussing practical aspects of phonon measurements. Of course, one does all the calculations beforehand to get the best conditions for measurements. But I would strongly urge you to keep some questions because day after tomorrow, I will take a tutorial and will like to clarify your doubts about the lecture so far on the introduction of neutron scattering or neutron inelastic scattering and quasi-elastic scattering and measurements of phonon dispersion curves, and something more that we are going to do in next half an hour. So, once this neutron inelastic scattering from periodic dynamics is done, then we will come to quasi-elastic neutron scattering or magnetic inelastic scattering in the remaining part. So, okay, let's move over to the inelastic neutron scattering from polycrystalline samples, phonon density of states. Now this is said either single crystals are not available, or you are interested in only getting a general information. Well, this is also relevant because with a single crystal, often we measure phonons along either some very high symmetry directions where there is a good selection possible between different phonons, along low symmetry directions, which are not along the, let's say, the crystallographic 100 kind of directions, but any arbitrary point in the Brillouin zone. The symmetry is not very high, and it's very difficult to separate out phonons which are in close in frequencies, and where the eigenvectors are also not very simple, like simple longitudinal or transverse or acoustic or optic. So, and for many thermodynamic properties, we are interested in getting the average phonon information. For example, even the specific heat is an average over all the phonons. So you need to get the phonon density of states to get the thermodynamic properties. And that is why, even if single crystals are available, we would like to look at the phonon density of states, and that is best done using polycrystalline samples. And now the coherent scattering, as we said, we can have coherent scattering as well as incoherent scattering. The coherent scattering gives you the collective dynamics. Incoherent scattering gives you the single particle or single atomic dynamics, the spectrum of vibrations of individual atoms, all summed over all the atoms. And in general, depending on the nature of cross-section, you have both. You have the coherent scattering and you also have the incoherent scattering. The coherent scattering part is usually analyzed in terms of incoherent approximation for polycrystalline samples. And this is possible when the Q, the wave vector, is larger than say typical 2 pi by r being the interatomic distance. So for the wave vectors which are fairly large, we can ignore the correlation between the motions of different atoms, and these correlations are very important for this. So, and therefore one can, if Q is so large, we can probably ignore the phase terms because we are summing over a large number of phonons. For this other reason why this happens to be the case is because let's say if you have a Brillouin zone, if you have the reciprocal lattice, so these are my, let us say, reciprocal lattice points, and if my Q is say so large or even larger than this, then around this point I can get the small q values from all the other g values. So you can, your small q can be this, it can be this, it can be this, it can be this, and so on. So a large number of small q values, small q vectors. See, for a given large q, the g is large, and all the points around. So a large number of phonons may be contributing to the same capital Q. And so on the average, one can ignore the phase relationships, and so that simplifies. This is called the incoherent approximation. In other things that we have is the directional averaging over Q is done. So Q dot xi square can be replaced by Q square xi square by 3. So with this approximation, the scattering from each atom is treated as incoherent, but with the same scattering amplitude, namely the coherent scattering amplitude. And of course, in addition, we also have the incoherent scattering. So what we assume is that now the scattering is proportional to the total scattering cross-section, or the net scattering length of the atoms, sum over the coherent and the incoherent part, or root mean square of this. So what you have is here is the coherent part plus the incoherent part. Okay, that gives me the total cross section, and so I will take the square root of it and call it bk, which is the effective scattering length, and so my total scattering will be proportional to this quantity, or the square of this quantity. Okay, so when we do that, so if I remove the phase terms and replace q dot xi square with this 1/3 of q square xi square, then I get this term, and in incoherent approximation, and then again, as we said, we summed over all the q around this capital Q, integrate over all the frequencies. So it becomes a somewhat much simpler expression. You have the okay, here we have just normalized it with the total scattering length for the entire sample over k. So de Beauvoir factor You have q square divided by the mass of the atom k, and the integral over the frequencies is the phonon density of state, what we call here the partial phonon density of state coming from the atom k. Okay, there are n atoms in the primitive cell, so each atom gives its partial component, and that is defined as the phonon density of state weighted by the corresponding displacement term for the atom k. So if this is defined, then the total intensity that we measure will be proportional to the sum over all the partial phonon density of states weighted by the scattering length square, the corresponding de Broglie factor, and of course the phonon population factor, which is always there. So once this data is there, it is possible to extract information about the density of state. You can see that we do not get the true phonon density of state, but you get what we get. It is a weighted phonon density of state weighted by certain terms here. Okay. This, of course, can be corrected very easily, so this is not an issue. All right, so this was what we said. So what we define here is a neutron weighted phonon density of state. There are various terms used here. Some people call it generalized phonon density of states, but I just prefer neutron weighted to say that yes, we are talking of a phonon density of state that is measured, which is weighted by the neutron scattering cross sections. Same thing if you measure by any other technique, say for example with X-rays, it will be weighted by the X-ray form factors of the elements and so on. So it's not a unique experimental quantity, but strongly depends on what is the probe that is used to make these measurements. So one can make these corrections here. Okay, here it is just written in terms of energy. So essentially you divide by the corresponding population factor. Once again, this plus minus is whether you are doing in neutron energy loss mode or neutron energy gain mode. One uses appropriate terms. However, here there is a major complication. Complication arises because of the de Broglie factor. Is not a constant. It varies. It also strongly depends on which atom you're talking about. Suppose it's a system in which you have a light atom and a heavy atom, and the mean square displacements or the thermal vibrational amplitudes are very different for the light and heavy atoms. Normally, the heavy atom tends to have a smaller value, and the light atom has a larger value. So de Broglie factors can be different. But experimentally, there is no way of, when converting this data into this, you can't take it out of the sum. So most of the time, people just assume an average value and use this such an expression and give you a neutron weighted density of states. But yes, one has to be careful in interpreting it. I would prefer it much better to say calculate theoretically and then compare at the level of SQ omega, keeping the de Broglie factor inside the sum rather than taking out an average value outside. But well, depends on what is possible. So that's one important thing that is done. Then there are also some. Okay, so that's let's see what I have here. So now, how do we make the measurements? Well, these are mostly the phonon density of states are better measured with the time of flight instrument, because we are not interested in scanning at each and every point in q omega space. However, if you are at a reactor and you have a triple axis spectrometer, then also you can do it. What we do is we make a large number of measurements at constant q So obtain S of QE at a large number of Q values and usually choose large enough values of Q so that the incoherent approximation is valid, and then take a suitable average over that. So, and in each can, again, similar to what we said in case of a single crystal, we can keep the final energy, for example, fixed, and vary only the incident energy and keep the wave vector Q constant and so on. So then if you scan as a function of energy, you will get a function which is like the density of state with this kind of analysis. Okay. There are just a few things I should just like to mention here. One is that if you make this measurement okay, we are doing it as a function of Q, but if Q happens to be equal to correspond to a break position, then you will get a huge elastic intensity because of the diffraction, and that will, the inelastic signal would be lost there. So while making these measurements as a function of Q, we should avoid regions which are close to the break positions. So we have to omit it anyway. That is one important thing. Other thing is about the sample thickness. See, if you, what is wrong? How much sample can one use? Quite often in neutron scattering, in typical instruments, we have the neutron beam size is about a few centimeters, maybe 4 centimeter by 4 centimeter. It's mostly rectangular, 4 or 5 centimeter in size. With a focusing monochromator, it may be down to 3 centimeters. So that the typical beam size is of the order of centimeters. That's one. And so you need to use samples which can make use of the full beam. So you will end up using maybe about 10 cubic centimeters of the sample, or smaller than that, depends. At spallation neutron sources, the beam sizes are even larger, and the instrument, the lengths are also very large to get the proper resolutions and so on. But what about the thickness? Can I use any arbitrary thickness to keep increasing my signal? No. The reason is that there is certain scattering cross-section, and if you use too thick a sample, you will get a multiple scattering. And multiple scattering inside the sample. Okay, what I mean by multiple scattering here is the following. Let's say my scattering cross-section is, say, 10 barns. A barn is 10 to the power minus 24 centimeters square. Now, typically, in typical sample, with about 5 millimeter of the sample, or around that number, the scattering is about 10%. Means out of the incident beam, 10% of the neutrons are scattered. So if I use more than that, then the chances are that you will have a first scattering, and then you also may end up having a second scattering. And then if you have a multiple scattering process, my signal may be corrupted. The corresponding spectrum that I may get will be a combination of the two. So often we choose sample thicknesses which give, say, around 10% scattering, and we can calculate it because we know the scattering cross sections, 4 pi b square, and we also know the absorption cross section and so on. So using those numbers, we can calculate, and it turns out to be in the region of a few millimeters, except for some highly scattering compounds containing, for example, hydrogen atoms. So typically for hydrogenous materials, the thickness that we use will not be like 5 millimeter, but 1 millimeter or even smaller at times of that order. Okay, so that's very relevant about the sample thickness. Other important thing is, as we said, in case of phonon scans, we were only interested in seeing get the position where the intensity is maximum. So the position where in case of one phonon scans with a single crystal, our interest was only to find the position of the energy and the wave vector where we get a good signal, and that would correspond to the phonon energy and phonon wave vector. However, here, in case of a polycrystalline sample, when we are trying to measure the phonon density of states, the intensity is very important. So, which means we have to measure the absolute intensities and make which are a function of again the various angles or the wave vectors. So this situation is similar to what you do in a diffraction. See, when you are trying to do a single crystal diffraction, then well, you don't worry about. Okay, there also you worry about the intensity because that will be proportional to the structure factor, and you need the structure factors to refine the crystal structure. With the powder diffraction also you need absolute intensities because you need to do a ritual refinement. In case of phonons, I need intensities only if I am trying to determine the eigenvectors. So, like in the case of diffraction analysis, but for otherwise for single crystal measurements, I don't really worry about corrections to the intensity. However, for the polycrystalline samples measuring phonon density of states, we are concerned about intensity corrections, and these are very important. Often the instrument in charge or instrument scientist would know about what kind of corrections are required. But as an experimentalist, you have to have some feel of it. How the corrections will depend on the various angles or the scattering angle, for example, or the wave vectors. One of the ways we do is by calibration. We may use a standard sample. Often it's a vanadium sample. And the vanadium, the good part is its coherent scattering cross-section is negligible. And because it has essentially only the incoherent scattering cross-section, there are no complications because of the structure or the collective dynamics. And therefore, the dependence on the wave vector is very simple. Okay, it's only maybe the Debye-Waller factor or what are some standard instrument parameters. So, which can be more easily corrected. So, vanadium is often used as a standard sample for calibration of the instrument. And with respect to that, we can see how these intensity corrections can be then made coming from all kinds of factors. Now, further than this, the next issue in with polycrystalline samples measuring phonon density of states is the multiphonon correction. Okay, before I go to multiphonon correction, let me just talk about this. We already mentioned about the problem associated with the Debye-Waller factor. So, as I said, Debye-Waller factor is extremely important, whereas in which you can only take care by using a good calculation of the lattice dynamics. Experimentally, in all the measured laboratories, they will give you they will reduce the data and give you as the neutron beta density of states by assuming that the Debye-Waller factor is an average term between all the atoms, and you can get the average term by some kind of an iterative process. That if you have you assume some number, get a phonon density of states. From phonon density of state, you can calculate what is the mean square amplitude of the atom, vibrational amplitude of atoms, and feed that number here, and again iterate it further. Computationally, you can calculate the phonon neutron weighted density of states by computing the partial phonon density of states from lattice dynamics and doing a suitable weightage with the scattering length and mass. So this is a factor. This again is a very important term because you can see that this is in the measurements with the, when you have several atoms in the unit cell, the weightage will be higher for those atoms which have a large scattering length and have a small mass. So quite often in oxides, for example, oxygen tends to have the largest component, and what we measure may be largely coming from oxygen atoms. Although other atoms also contribute, but that number is often smaller, and so that's very important. I mean that you what you are measuring, the phonon density of state will be largely coming from, for example, the oxygen atoms and not so much from other atoms. Unless there are regions in the energy spectrum where oxygen does not contribute and only other atoms contribute, so those may still be visible. Okay. Now, let's look at the remaining issue, that the multiphonon correction. Multiphonon correction is a very important issue in phonon density of state measurements, and that's because we are looking at the entire spectrum, and so particularly the low frequency modes multiples of those will also be seen at higher energies. What this conceptually it is simple. The energy change, neutron energy transfer, could be not just one excitation, it could be more than one excitation. And the wave vector also is correspondingly like this. So that means for a given Ki and Kf, there are several combinations possible. So this is okay. But now because we have a large number of possibilities, the multiphonon spectrum tends to be relatively smooth. It may not have very sharp peaks, well, but it could. I mean, it's not always ruled out, unless there are really some very dispersion-less phonon branches, then they could give some sharp peaks. And multiphonon's contribution is also important at small temperatures because in neutron energy loss process, you can create not just one excitation, but more than one excitation also. Okay, so once again, the incoherent approximation is used. The analysis is fairly straightforward. You have a one phonon spectrum, which is just the phonon density of states. Then this is just elastic scattering. And then you can do a convolution 2 times or 3 times and so 4 times. And you can create spectrum corresponding to multiphonons, so 2 phonon, 3 phonon, and so on and so forth. And this is all done. And then finally, you can sum over all of it, and that will give you the total spectrum. And so accordingly, then one can make a suitable correction. So one can calculate the one phonon term, and then we can also calculate the total multiphonon term from theoretical calculations. Experimentally, if you have the experimental data, okay, it is, some analysis can be done in an iterative manner, and it is also done that way. Now, what are the weightage of these various terms here? These are, as we mentioned the other day, the corresponding proportions are if one phonon, as we said, no, the one phonon term is proportional to q square u square. Then second, higher phonon terms are proportional to and so on and so forth. Okay, so you can see that if my q is not very large, if q is very large and if this term itself is greater than 1, then higher phonon terms are also going to be very significant. However, if this is less than 1 or so, then you can see that the higher phonon terms will decay fast enough, and so you will not have too many terms. So therefore, on the one hand, we said that we want to use a large Q to get good intensity, but there is an optimum. If your Q is very large, then your Debye factor will kill the intensity, and also there will be a large contribution from multiphonon terms. So ideally, it's ideal to choose some intermediate values. Typically, you can say Q square, U square being of the order of 1. In that case, the one phonon terms will be dominating or significant, and the corrections will be minimal. Okay, so I think I like to more or less end here today. If there are any questions or so, let's take them. Okay, sorry, just one more example. This is just an example of a data taken at the Dhruva reactor of the phonon density of states in a sample of nickel silicon. It's not a very complex structure. So that's the measurement. And here there is a calculation also which has contribution. The silicon nickel contribution is given by the blue term. So as you can see here, nickel has a large contribution and the silicon has a smaller contribution. And what you measure is actually the sum total of the two. That is the theoretical calculation based on the density functional theory. It's not perfectly matching with the measurements at high energy region, but in the low energy part, the first peak measures very well. Now this could be because the wave vectors, there is no proper integration of the wave vectors or something, but overall one gets a decent feel of the spectrum. Okay, and then this very same calculation was also used for understanding some anomalous thermal expansion in these materials. Okay. All right, so with this, I think I end it today. And if there are questions, I think let me know. Are there any questions or comments from today's talk? So there is a question? Okay. Sir, in resolution ellipsoid is obtained from deviation from Q omega. So from experimental data, do we obtain? Yes. The answer is yes. So see, if the resolution ellipsoid were entirely symmetrical, so in general, what we measure is a convolution of the Q omega, or say the dispersion surface and the resolution ellipsoid. Now, in such a convolution, you can have the peak values shifted from the dispersion surface. So it does happen, and one can use some computer programs or something. So there are deviations, and we need to really make corrections for it in the experimental data. Okay, I'll give a little more detail of it maybe in the tutorial. But yes, the short answer is yes. There are shifts, deviation in the Q omega values because of the resolution ellipsoid, and there is certain curvature. Main problem is the dispersion surface is not flat, and if it has a curvature, then yes, the convoluted values may be shifted from the chosen Q omega middle values. Yes. Is there any other question? No. Fine. Then let me thank you very much for this today's. Yes, please give your questions. Otherwise, I'll plan something of my own for the tutorial day after tomorrow. Thank you.
Just announcement. I'll just make an announcement. You done? Hello friends, there's an announcement that the assignment regarding magnetic neutron scattering, I'm sorry that I couldn't upload it till this morning, but now it is uploaded at anuvidya.in. My request that you please download it from anuvidya.in, and people who are desirous of getting credit points, they should submit it at the earliest possible. Dr. Anil Jain will evaluate this particular this particular assignment, and he will get back to you. And now you can see that the inelastic neutron scattering, it's a little involved, and my request has always been to you that please ask questions, please to at neutroncourse@gmail.com, so that I can pass it on to Dr. Chaplot, and Dr. Chaplot can understand where the communication is lost or you are not able to understand, so that it becomes clear to you. There are issues, because there are issues regarding eigenvectors, regarding phonons. We know that in your master's course you haven't gone through phonons in such great details, and now we are talking about how to measure phonons, at which eigenvectors, at what q values. It might confuse you, but my request to you, please ask questions so that we can clarify those things, because we don't know in which direction the confusion is. Thank you. Coffee?